everyone. Today, me, alongside my group 2, will cover this topic, which is maximizing profit from two products using multivariable optimization in business decision making. The question we're answering today is very simple. If a company produces two products in which they share the same limited resources, how many of each should they produce in order to yield maximum profit? Knowing this problem, let's set the scene, shall we? So let's say a company produces product A and product B. Here's the catch. They both share the exact limited resources, labor, materials, and machine time. If we use more labor to produce product A, product B might not have enough. If we put more materials into producing product B, product A might not have enough materials. The manager's job here is to find the perfect balance. But if they rely solely on their intuition, there's a possibility that they end up overproducing a product, which could lead to real financial consequences, where they waste resources and lose money. So that's where we step in. Instead of guessing, we'll build a mathematical model and use calculus to find the exact answer that yields the maximum profit. So knowing the problem, let's go into the concepts that we will use. The first concept is function of two variables, turning our business problem into an equation where we find the total profit, which depends on x and y. The second one is partial derivatives. Why not use regular derivatives? We use partial derivatives because our profit here depends on two variables. So using partial derivatives, we can adjust the rate of change for A separately and for B separately. The next one is critical points. This is used to find the best production mix. And then we'll use second derivative tests. We use the second derivative test to confirm that the answer that we found is indeed a maximum value. So knowing all of the concepts that we will use, I'll pass this to my friend Madhyar.
Thank you, Aaron. My name is Madhyar, and I will walk you through how we build the mathematical model, sample of mathematical model. We define two decision variables here. X represents the number of units of product A produced per day, and Y represents the number of units of product B produced per day. Here in our sample, product A sells at 50 ringgits per unit and product B sells at 40 ringgits per unit. So our total daily revenue is simply R of X and Y equals 50X plus 40Y. This is a linear revenue function, straightforward so far. Now it gets more interesting. The cost function is not linear. We modulus that x of x and y as c of x and y equals to x squared plus xy plus y squared. Why non-linear? Because in real production, the more you produce, the more expensive each additional unit becomes. This is called diminishing returns, captured by the squared terms x squared and y squared. The term cross term xy captures the fact that producing both products at the same time shares and competes for the same resources, which drives up costs. This is much more realistic model than a simple straight line. Here then, putting it all together, our profit function is P of x and y equals revenue minus cost, which gives us P of x and y equals 50x plus 40y minus x squared minus xy minus y squared. This single equation now captures the entire business problem. So our goal is to find the value of x and y that makes P as large as possible. Because P depends on two variables, we cannot use a single variable derivative, so we need partial derivatives that we learn in calculus 2. A partial derivatives allows us to differentiate with respect to one variable which keeping the other fixed. For example, the partial derivative of p with respect to x tells us if we produce one more unit of product A, um, how does profit change? And the partial derivative of p with respect to y tells us if we produce one more units of product B, how does profit change? The maximum profit occurs at the point where both partial derivatives equals zero at the same time. So that's our target, and I now pass it to Nani, who will carry out the full calculation. Thank you.
Hello everyone, I am Tamatam Krishna Snehidgad. My ID number is CST25091110. So today I am going to explain about finding partial derivatives. So the first example is the profit function for two products is this equation. So in this equation, px of y is equals to 50x plus 40y minus x square minus xy and minus y square. And from this, we are going to derive with respect to x, the partial derivation with respect to x and partial derivation with respect to y. So the first one, partial derivative with respect to x. So when we partial derivative with respect to x, the y terms is going to be the constant. So if we partial derivative with respect to x, the y terms is going to be 0. So the equation gets to be 2x plus y is equals to 50. And the next one, the partial derivative with respect to y. And in this scenario, the x terms will be 0. So finally we get the equation 2x plus 2y is equals to 40. And we can observe this slide, uh, the partial derivative shows how profit changes. So when one variable changes while other remains constant. So in these two scenarios, with respect to x, the y is going to be constant. With respect to y, the x is going to be constant. So with these two equations, we are going to find the critical point, and the critical point setting both equals to 0 locates to the critical point, and we are going to do in the next slide. And the next slide, finding the critical point. So let's start. These are the two equations. The system 2x plus y is equals to 50 and x plus 2y is equals to 40. These are the two equations we got in the previous slide. So by the substitution method, we get x is equals to 20. There implies y is equals to 10, and these are the 2 points we got. And the product A is going to be the x 20 units per day, and product B going to be the y, which is 10 units per day. And we got the critical point, so x comma y is going to be the critical point, so 20 comma 10 is the critical point. In this slide, we're going to know that calculus transforms a business problem into a precise, which is mathematically proven decision. And going to the next slide, second derivative test and maximum profit. So the first one, second derivative test, from the x and y. So the second derivative test of p with respect to x and with respect to y with respect to xy, and these are the going to values minus 2 and 1. By the determinant, we get this 4 minus 1 is equals to 3, and which is determinant is greater than 0. And the first term, the second derivative test of p with respect to x is less than 0. So the scenario goes to be the point 20 comma 10 is going to be the local maximum is confirmed. So the next is maximum profit. So we are going to calculate the maximum profit. As it is simple, the equation which we got in the question is the equation we are going to substitute x and y. So p 20 comma 10, we are going to substitute 20 10, and we get the values. And by the simplification, we get 700 ringgits per day, and we can know in the conclusion, product A is 20 x, which is x 20 units per day, and product B is y, which is y is equals to 10 units per day. And finally we got the maximum profit, which is 700 ringgits per day. So that's the maximum profit. That's all. And Abhi will explain the results part and the conclusion. Thank you.
Respected lecturer, my name is Abhinav. and I'll be presenting the final part of our presentation, which includes interpreting the result, limitations of model, and the conclusion. Now, interpreting the result. As my groupmate explained earlier, after solving the equations using partial derivatives, we got value x equal to 10, x equal to 20, and y equal to 10. Here, x represents product A and y represents product B. So, the best production plan is to understand 20 units of product A and 10 units of product B per day. Now, to understand the maximum profit, we substitute x equal to 20 and y equal to 10 into the profit function. The profit function is, as you can see on the screen, px of y equal to 50x plus 40y minus x square minus xy minus y square. Now, we can divide the equation into two equations. Like one is 50x plus 40y and another is x square plus xy plus y square. If we calculate both individually, we get one is 1400 and one is 700. When you minus cost from the revenue, you get total profit. As you can see on the screen, 1400 minus 700 gives 700 ringgits per day as a profit. This is why our slide shows the maximum profit is 700 ringgits per day. This result is reasonable because product A earns more than product B. But at the same time, if we produce too much, the cost also increases. So the answer gives a balance between revenue and the cost. That is why we can say that this is the best production plan. And now we go on to the limitations of model. Even though our answer is mathematically correct, the model is still simplified. The first limitation is simplified costs. In our model, the cost is represented using a simple function, but in real life, real business, cost includes many more, like things like labor, machines, rent, electricity, and raw materials. And the second limitation is no capacity limits. This means we did not include limits on labor hours or machine capacity, but in real life, companies include them. The third limitation is the model is for one day only. It does not include long-term planning, storage, demand, and changes in the market, but company includes them. Another is fixed prices. In our model, product A is always 50 ringgits and the product B is always 40 ringgits. But in real markets, prices change because of demand, competition, or discounts. So this model is useful for understanding the idea of the optimization, but real life businesses need much more information before making a final decision. And when we go to the conclusion, to conclude, a project shows how calculus 2 can be used in business decision making. Our profit function was 50x plus 40y minus x square minus xy minus y square. Using partial derivatives, we found the best plan. 20 units of product A and 10 units of product B per day. At this point, the maximum profit is 700 ringgits per day. So the main idea is that calculus helps us to turn a business problem into a clear and proven decision. Instead of guessing how much to produce, we can use mathematics to find the best answer. And that's all for the conclusion. Thank you.